Greetings. We will look at the spectrum of the hydrogen atom or any alkali atom, anything in the first group of the periodic table. They all have similar spectra in some respect. Of course, they are different in details, but there are several common features, and when we examine the spectrum of the hydrogen atom, it does set up the procedures which we must employ in interpreting the spectra of bigger atoms. So, we considered the strong field effect and the Paschen-Bach effect, and then our active consideration now is on the study of the weak field Zeeman effect. And at these magnitudes of the applied magnetic field, the spin orbit interaction is the dominant interaction, because the magnetic field, the applied field is weak. So, the internal effects take over, and J and M are the good quantum numbers and not ML and MS. The eigenstates are not eigenstates of LZ and SZ, but they are eigenstates of J square and JZ. So, that is what led us to determine the perturbative correction to the original unperturbed energy, and this correction requires us to determine the matrix element of SZ. Now, the difficulty here was that the quantum states that you are considering are eigenstates of J square and Jz and not of Sz. So, that is the reason we had to find some mechanism to get this matrix element, and we found using two alternative procedures, one based on vector identities for vector operators. Okay, these are operators for which are irreducible tensor operators of rank 1. So, we use those identities, and the other procedure which we followed was based on the Wigner-Eckart theorem, and using both the procedures we are left with we are led to a relationship which gives us the matrix element of an arbitrary vector operator, no matter what it is, and you get it in terms of V dot j and j. And if this V happens to be our S operator, the spin operator, then we can use it and apply it for this case. So, we have S equal to V in our case. So, now we get h cross square j into j plus 1, and here this matrix element is the matrix element of the spin angular momentum S, and this is equal to the matrix operator matrix element of the operator, and there is a scalar part which is S dot j, and there is a vector which is the angular momentum itself. So, this is the S dot j j operator. So, now this part we can write this relation for each component, because this is a vector relation and there are corresponding relations for all the three components Sx, Sy and Sz, or you can write it for the spherical components as well. And now the relationship for the Z component is that you take the Z element of this operator, on the right side S dot j is a scalar, so it remains as it is, and you have the Jz operator, and what comes out of this part is that Jz operates on J Mj, and you will get Mj times H cross. Okay. So, that is a big advantage here, you get Mj times H cross coming out of the operation by Jz, and this S dot j can again be written in terms of operators whose eigenstates are already involved in the basis set, because the operator S dot j is nothing but j square minus L square plus S square, because L plus S is what gives you j. So, S dot j turns out to be j square minus L square plus S square. So, all you do is to take the square of S plus L equal to j. So, dot out S plus L with S plus L, and this is exactly what you will get. So, you have the operator S dot j whose matrix element now you need, this is given by a sum of 3 operators j square minus L square plus S square by 2, but now this state is an eigenstate of these operators. Okay. So, what are the eigenvalues? So, you get h cross square into j plus 1 minus L into L plus 1 coming from here and S into S plus 1 coming from here. So, you get numbers on the right side now, and you are able to solve this expression, and this matrix element, which is the matrix element for Sz, is now obtained completely in terms of these quantum numbers, and you can write it for this matrix element, which is what you need. So, you cancel this h cross square with this h cross square, move this j into j plus 1 to the right, it comes in the denominator, and this is the result that we were looking for. This is precisely the term that you needed to get the correction for the weak field Zeeman effect. So, this is the correction now. This comes along with the other term which was coming from the j term itself, and together with this gives us the correction, the perturbative correction when the magnetic field is weak and the spin orbit interaction takes over. So, that is the dominant interaction, and this is the energy correction that must be applied. So, this is the expression that we were looking for, and we have now been able to resolve it. So, this is the energy correction, the h cross cancels, and if you combine these two terms, there is a Bohr magneton times the magnetic field in both the terms and mj in both the terms. So, you extract this as a common factor, and you have 1 plus g j plus 1 minus L into L plus 1 plus S into S plus 1 divided by 2j to j plus 1. So, there is, this is the Landé's factor exactly. So, this is like g. Okay. This takes exactly the same place as g did for the case of the orbital angular momentum and also for the spin angular momentum, because there is a corresponding magnetic moment associated with the spin angular momentum and with the orbital angular momentum, and this is the effective g coming from the combination. Okay. And this is neither equal to 2 nor equal to 1, but it depends on the values of j and L. S is always half, of course. Okay. S for electron is half, so it is half into half plus 1, and this factor is what is called as the Landé's g factor, and this is what governs the energy splitting between the perturbed levels as a result of the magnetic field which is applied and treated perturbatively when it is relatively weak, and you can use the j mj quantum numbers. So, which quantum numbers are the appropriate quantum numbers to be used is the dominant consideration here, and once you take the right basis you get the right results, but the choice of the basis is the critical factor here. So, this is a very similar expression for just the way we had the magnetic moment, which is proportional to the angular momentum. You have got the same kind of consideration, but with a different value of g, which is given by the Landé's g factor. So, now the spin orbit interaction is S plus L, right. So, S plus L gives you the total angular momentum j, which can be either L plus half or L minus half. So, you can put in the values of j, the possible values of j, which is either L plus half or L minus half. So, there are two possibilities here, and for every L for every j you put these two alternative values, and you find that the energy correction depends on whether j is L plus half or L minus half, and accordingly the correction is either 1 plus 1 over 2 L plus 1 or 1 minus 2 L plus 1. I have certainly used S equal to 1 half in the getting this expression. So, when j is L plus half, the correction goes as 2 L plus 2 over 2 L plus 1. When j is L minus half, the correction goes as 2 L over 2 L plus 1. So, this is the resolution of the energy levels under the application of the magnetic field. If you look at the NP state, okay, this is like the 2p state in the hydrogen atom if you like, or the 3p state in the sodium atom, okay, or if you take any of the group 1 elements, the outer electron is the ns1, and when it gets excited to the np level. So these are the levels which are involved in the sodium atom spectrum, the famous D1 D2 lines of sodium. They come from the transition to from 3p 3 half and 3p 1 half to the 3s level, right. But now the 3p 3 half level will get split into these 4 levels, and the 3p 1 half level will get split into these 2 levels. So you will have the D1 D2 lines split into very many lines, and the same thing will happen to all the alkali atom spectra, okay. So the rubidium spectrum or strontium or anything in the first group, they will show these features. So this is the resolution of the spectra. So NP 3 half splits into these 4 levels, J is equal to 3 half. So Mj can go from minus 3 half to plus 3 half in steps of 1. So you have minus 3 half, minus half, 1 half and 3 half. So these are the 4 levels into which the NP 3 half state splits, and the NP 1 half state splits into these 2, which is corresponding to Mj equal to minus half and plus half, and likewise the Ns half spectrum splits, the Ns half level splits into these 2 corresponding to Mj equal to plus half and Mj equal to minus half, and the D1 D2 lines split into 10 lines. So what were originally only 2 lines now will show up as 10 lines. So there are 4 lines coming in from NP 1 half, and we are sketching those lines which correspond to the dipole selection rules, okay. So the lines which are possible under the dipole selection rules, there are 4 lines which come from the NP 1 half, but NP 1 half is no longer a single level, there are 2 of these. So 2 come from the upper level corresponding to Mj equal to half, and 2 come, the line number 2 and 4 come from the lower level which corresponds to Mj equal to minus half. And likewise the transition from NP 3 half splits into these 6 lines, and these are the 6 lines which come from the NP 3 half levels. So these are all the transitions which take place corresponding to the dipole selection rules. Now the question is, first of all we have to write these quantum states for J Mj quantum states in terms of the ML MS basis, okay. So these are the J Mj quantum numbers. So L is equal to 1 for P, for NP, for all the p orbitals L is equal to 1, S is always half, J for this state is 3 half, and Mj for this state is 3 half. So these are the LS J Mj quantum numbers for this uppermost level. For the next level, the LS J Mj quantum numbers are 1 half, 3 half and 1 half. The last quantum number is the Mj quantum number, okay. And this way you can write the J Mj quantum numbers for all of these 10, these 4 and to 6 and to 8, there are 8 levels for which you must identify the quantum numbers, and these are the LS J Mj quantum numbers for the p states, and then for the s states L is equal to 0 for the s orbital. So L is 0, S is always half, and J is always half because L is 0, okay. So J can take only one value which is half, and Mj can take 2 values which is either plus half for the upper one and minus half for the lower one. So these are the LS J Mj quantum numbers for these 8 states, and you can write these quantum these coupled vectors J Mj in terms of the ML MS basis by looking at the Clebsch-Gordon coefficients, right. So here you are coupling L with S, and S we know is half. So the appropriate table to be used is the table number 1 from Corner and Shortley, which we have with us, okay. It is also uploaded on the course web page. So this is the table of the Clebsch-Gordon coefficients that we can use, and using these tables we can write the j m j quantum numbers in terms of the uncoupled direct product of uncoupled vectors. So let us illustrate this for one of these. So let us take the case when j is 3/2 and mj is 1/2, just to illustrate one of these. And what will this be? So you are expanding it in the uncoupled basis along with the Clebsch-Gordon coefficients, right, and here is a sum over ml going from -1 to +1 and ms going from -1/2 to +1/2. So how many terms will we have on the right hand side? 3 into 2, we will have 6 terms, okay, but the Clebsch-Gordon coefficient will vanish unless mj is equal to ml plus ms. So out of the 6 terms you really do not have to find the Clebsch-Gordon coefficient for all the 6 terms. You have to you can find the coefficient only in those cases for which ml plus ms will give you mj, and that means that there are only 2 terms which you need to consider, and these terms are those corresponding to ml equal to 0 and ms equal to half, or ml equal to 1 and ms equal to -1/2. So these are the only 2 terms that you need to consider, because both of them give you ml plus ms which is equal to half, which is the value of mj here, okay. So now you need to find the Clebsch-Gordon coefficients for these 2 terms only, and let us take one of those. So let us take the case when ml is 0 and ms is equal to half. So for this, what is the value of the Clebsch-Gordon coefficient, and you have to find the corresponding Clebsch-Gordon coefficient also for the other case in which ml is equal to 1 and ms is equal to -1/2. So these are the 2 coefficients that you want to determine from the table. So let us take one of these and notice that ms is equal to half. So you can look at the first column here, right, this is the first column since ms is half, and then look at how j is related to j1, and you find that you have j equal to 3/2, this is the value of j which is 3/2, and it is coming from j1 plus 1, right. So when do you have j equal to j1 plus half? You have it in the first row. So first row and first column is what you must look at. So this is the matrix element that you must look at, and all you now need to do is to plug in the quantum numbers in this formula for the Clebsch-Gordon coefficients. You can always determine the Clebsch-Gordon coefficients from first principles using the recursion relations that you have learned, but these Clebsch-Gordon coefficient tables are available in on all books in quantum mechanics. They are available on the internet, they are available as Clebsch-Gordon coefficients or as nj symbols and so on. So you can take it from any source and then plug them in. So this, after you plug in these quantum numbers, so j1, m and half, so you put 1, half and plus half, and you find that this coefficient turns out to be √2/3. Now you need the other one, and in this case ms is -1/2, so you must look at the second column instead of the first column, but then you continue to have j equal to j1 plus half. So you look at the first row, and this is the formula that you must use. So what do you get from this? You get √1/3. Actually you could have guessed that, because the sum of the squares must be equal to 1, okay, but then you would not have gotten necessarily the correct phase. So that is why you have to use this table, okay, otherwise you will not get the right phase. You would get the magnitude √1/3 from the normalization, but not the phase. It could be either plus √1/3 or minus √1/3. So normalization cannot be used as the method to find the coefficient, it should always be used as a check, because if you get this wrong, the normalization would tell you that it is wrong. So these are the 2 coefficients that we needed, one is √2/3 and the other is √1/3, and using these coefficients in this expansion, so out of these 6 terms only 2 terms will contribute. These are the 2 terms, okay, and when you see so many numbers sometimes you feel dizzy, and that is when it helps to look at these angular brackets, because this side has got a rounded bracket, this side has got an angular bracket. Okay. So, you keep track of which was the uncoupled part and which is the coupled part, because that is part of the reason when I introduced the Clebsch-Gordan coefficients at the very beginning, I used this notation, not that it is mandatory, most books do not use it, but it is very useful when you look at expressions of this kind, because there are so many numbers and you really feel dizzy as to what is what and which side is what. So, it helps to keep track of which is the this is the angular bracket here, no, this is the circular bracket and this is the angular bracket here. So, you know that this is the uncoupled part. So, this is the ML, MS, and you know that this is J and MJ. Okay. So, when you are dealing with practical applications, a notation of this kind is sometimes useful, which is why I introduced it in unit 2. So, these are the two terms and this is your expression for this state, but then there are you can write it in not just the Dirac notation, you can also write it as in the Schrodinger notation as well, because what you have for L equal to 1 and ML equal to 0 is the spherical harmonic YLM, which is the spherical harmonic for L equal to 1 and ML equal to 0. So, likewise this is also the spherical harmonic for L equal to 1 and ML equal to 1, and this is 1 minus half. So, this is really the spin down state and this is S equal to half and MS equal to plus half. So, this is the spin up state. So, the first term is a product of the spin up state, which I have written as alpha. Okay. The second term involves the spin down state, which is beta, and then you have got the spherical harmonics y10 coming from this 1 and 0 and y11, this is L equal to 1 and ML equal to 1. So, you can write this as a linear superposition. This is of course the coordinate representation of this vector, but you can go from the Dirac notation to the de Broglie Schrodinger notation back and forth just by taking the coordinate representation of the vector. So, this is the linear superposition of the J MJ states. So, let us write these for all the 8 states that we are concerned with. Okay. We found that the 2p 3/2 splits into 4 states, 2p 1/2 into 2 and 2s 1/2 also into 2. So, there are a total of 8 states for which we should write this expression. 4 of these come from our 2p 3/2, and by getting the coefficients you can write this directly. There is only one term over here, there is only one term which can contribute to MJ equal to 3/2, there is none other. So, this is unique, this is therefore this has got a coefficient of 1, and then you have MJ equal to 3/2, 1/2, minus half and minus 3/2. So, MJ equal to half will give you this, MJ equal to minus half will give you a similar linear combination, but notice that this is a superposition of alpha y1 and this is beta y1 plus alpha y1 minus 1s. Okay. So, this is a different superposition and you know how to get it. I have illustrated it for one of these and you can use the same procedure, use the Clebsch-Gordan coefficients and get all the states written explicitly. So, MJ equal to minus 3/2 again is a unique contributor to this, which has got a coefficient of unity, which is beta y1 minus 1. What about the 2p 1/2 states? This has got 2 states, one with MJ equal to minus half and the other with MJ equal to plus half. So, this is what you get for MJ equal to plus half, and then you get another term for MJ equal to minus half, which is a different combination. Mind you, you have got a minus sign here and a minus sign here. So, the phase of the coefficients is of importance. Okay. And this is the phase that you would miss out if you did not use the Clebsch-Gordan coefficient tables correctly. So, these are the 2 states for 2p 1/2 and likewise there are 2 states for the 2s 1/2. So, that gives us all the 8 states. Okay. And now you can look at the transitions between various states. These are the 10 transitions which take place between these 8 states, as we have seen according to the dipole selection rule. And as a spectroscopist, as an experimentalist, when you carry out your observations, you would be interested in looking at the intensities of these lines. Okay. If there is a transition, first of all there will be a certain intensity that you will measure. If there is no transition, the corresponding intensity would vanish, and you will need to calibrate your spectrometers, right. You will be measuring intensities on a certain relative scale when you do the calibration and so on, and you will be interested in comparing the intensities of transitions from one initial state to a final state, and that is affected by the transition matrix operator. The transition operator here is omega. So, this is just a generic expression for an interaction omega which is responsible for the transition from I to F, and what this matrix element gives you is the probability amplitude that this transition will take place. Its modulus square will give you the probability, and when you multiply it by appropriate constants and so on, you will get the line intensities, right. So, the information about the intensity of the spectrum is contained in this matrix element, and we know that this matrix element by the Wigner-Eckardt theorem can be factored into a physical part, which is the reduced matrix element, and a geometrical part which includes the Clebsch-Gordon coefficients. Okay. So, to get the transition intensities, if you just look at the Wigner-Eckardt theorem, it would seem that you will need not only the Clebsch-Gordon coefficients, but also the reduced matrix elements, okay, because this matrix element has got these two factors, and on the face of it, it would appear as if you will need both the reduced part as well as the geometrical part. Now, this as it turns out is not necessary if you are interested in comparing the line intensities, which is what the common interest often is, because anyway there is a certain calibration which is involved, there is a certain normalization of the intensities, these intensities are normalized with respect to one of them, and then you really measure the ratios of intensities. So, we will now study this question, that do we really need the reduced matrix elements, okay, and in some cases in spectroscopy, in a good number of cases, you really do not, because when you take the ratios they get cancelled out, and that is what we are going to discuss now. So, let us take two of these spectral lines. So, we will take, just to illustrate this argument, we will take line number 5 which is from this level to this level, and take line number 10 which is from this level, which is 1 1 1 half 3 half 1 half to, where does it go, it goes all the way here, which is the lowest level, which is 0 half 1 half minus half. Okay. So, let us take these two cases. The first one is line number 5, which is a transition from 1 half 3 half minus half to 0 half half minus half state. So, these are the expressions in terms of the uncoupled basis, right. This is the matrix element that you want to study. This is the transition matrix element, this is the transition operator, whatever it is. We know that these transitions in the dipole approximation are induced by an operator of rank 1, and that is all you really need here. You do not even need its explicit form, okay. All you need is that it is a dipole, it is a vector operator of rank 1. It does not matter if you are looking at the length form of the matrix element or the momentum form of the matrix element, it does not matter, because the only thing that is of importance is the rank of the operator. So, this rank of the operator is 1. So, you are going to put k equal to 1 in your Clebsch-Gordon coefficients, okay, and this is one of the transitions that we will study, and we will compare its intensity with the intensity of line number 10, which is a transition from 3 half 1 half state to 1 half 1 half. Okay. So, let us see how this works out. So, this transition matrix element is represented by this operator, which typically is the dipole operator, okay, operator of rank 1, and this is the operator which is sandwiched between the initial state and the final state, and you have got a similar expression for line number 10. So, let us first take the line number 5, and this is the matrix element that you want to study. Now, this matrix element, this is the matrix element of an irreducible tensor operator of rank 1. You can resolve it using the Wigner-Eckardt theorem as a product of the physical part, which is the reduced matrix element, and we have defined it with the root 2j plus 1 in the denominator, but you can define it differently also, it does not matter. So, this is the reduced matrix element part and the geometrical part, which is the Clebsch-Gordon coefficient. Okay. And this Clebsch-Gordon coefficient, what do we know about the Clebsch-Gordon coefficient? Whatever quantum numbers we know, we should plug them in. So, we know J1, which is 3/2, we know J2, which is the rank of the operator, which is k, and we know that it is equal to 1. We know that M1 is equal to -12 in this state, right. This is M1, this one, and we know these quantum numbers. What we do not know is M2. Okay. So, since we know that we are coupling angular momentum J1 equal to 3/2 with J2, which is equal to 1, J2 comes from the rank of the tensor operator which is responsible for this transition, you will use table number 2 from Karnan shortly. Okay. So, this condition however must be satisfied, that M1 plus M2 must be equal to M. So, this tells us that Q must be equal to M2, because both of these are -12. Okay. So, M will have to be 0. So, M2 will have to be 0, right. So, Q must be 0, and you can plug in Q equal to 0 over here. So, this comes from the selection rule which makes a Clebsch-Gordon coefficient non-zero. Okay. So, you use everything that you have learned and put it all together. So, you have this table 2 for J2 equal to 1, and we have got all the necessary quantum numbers. We have M2 equal to 0. So, M2 equal to 0 means that you should use this middle column here, right. And what else do we have? Now, we need the relation between J and J1, and what is that? This is the third row that you must use, because J is equal to J1 minus 1. J1 is 3/2 and J is 1/2. So, 3/2 minus 1 is equal to half. So, this half is equal to 3/2 minus 1. So, you must use the third row, and this is the coefficient that you need. So, now plug in the quantum numbers J1, M and so on, and that will give you the value of the Clebsch-Gordon coefficient. It comes with an appropriate sign, and if you just plug in the numbers, it turns out to be minus root 1 over 3. Okay. So, this is the coefficient you needed to write the geometrical part of line number 5. This is the physical part, this is the reduced matrix element, times the geometrical part, which is root of 1 over 3 with a minus sign, and we will now ask what is the corresponding expression for line number 10. And for line number 10, this is the transition for line number 10 from 1/2, 3/2, half to 0, half, half and half. Again we know that k is equal to 1. So, you break it into the physical part and the geometrical part, put in the quantum numbers, put k equal to 1 over here, find that in this case also the M2 quantum number must be 0, for the same reason that in the previous case you had both M1 and M equal to -12. In this case both M1 and M are equal to +12. So, there is a similar but a different reason which is responsible for the fact that M must be 0, and using the table for J2 equal to 1, you know that since M2 is equal to 0, you use the middle column, which is the column for M2 equal to 0, and then you see this difference. This is J equal to half, this is J1 equal to 3/2, the difference is 1. So, it is J1 minus 1 which will give you the value of J. So, again you must look at the third row and you look at this expression and plug in the quantum numbers, again it turns out to be root 1 over 3, okay, with a minus sign. But for a different reason. Okay. In the previous case, you had two factors in the numerator under the under root, and the first factor was 3 half plus half and the second factor was 3 half minus half. In this case, these two positions are swapped, okay, but the numerical value turns out to be the same. So, this is the matrix element which you have factored into the reduced part and the geometrical part, which is minus of 1 over root 3. For line number 5, we had already found out what the factorization was, and here also you had minus of root 1 over 3. So, what is our conclusion? When you take the modulus square and take the ratios, the root 2j plus 1 would cancel. That does not surprise us because they could have been absorbed in the definition of the reduced matrix element anyway, but then the reduced matrix elements themselves cancel. It is the same reduced matrix element which appears in both. Okay. So, the ratio is then given only by the ratio of the Clebsch-Gordan coefficients. So, without looking at the explicit form of the reduced matrix element, and we have discussed the explicit form of the reduced matrix element in some cases. For example, when we studied photoionization, we actually determined those integrals, right. We plugged in the dipole operator, found what is the transition probability from the initial state to the final state, we put in the radial functions for the hydrogen atom, right. So, all of that had to be explicitly done. In this case, we have not had to do it. So, without even looking at the reduced matrix elements, by taking advantage of the Wigner-Reichardt theorem, we find that those terms which contribute to the reduced matrix elements, they cancel each other, and then all you need to consider are the ratios of the Clebsch-Gordan coefficients. In this particular case, they happen to be equal. So, we can conclude easily that the spectroscopist is going to see these lines to be equally intense. So, without actually measuring, without actually calculating the reduced matrix element, which otherwise is certainly required when you look at this matrix element, because this matrix element is given by a term like this. There is a transition with this operator is responsible for, which effects a transition from an initial state to a final state, and if you were to determine this explicitly, you will certainly have to evaluate all the space integrals. But by exploiting the Wigner-Reichardt theorem, we could factorize this matrix element into two parts. The first part is the reduced matrix element, second is the geometrical part, and then we find that when you are looking at comparison between the intensities of various lines, which is the most common situation that experimentalists are concerned with the spectroscopists are concerned with, because anyway they are going to do some standardization with respect to some normalization. So, this normalization can also be absorbed in the normalization when you do the calibration of the intensities. So, this is the power of the Wigner-Reichardt theorem, which is an extremely powerful theorem in all branches of spectroscopy, whether it is atomic spectroscopy, molecular spectroscopy, nuclear spectroscopy, no matter what. When you look at transitions of condensed matter from one state to any other, the Wigner-Reichardt theorem turns out to be an extremely powerful one, and it gives you an excellent, very powerful handle on estimating the intensities of the transitions. But then of course, there is more to follow. That we started out with this non-relativistic Schrodinger equation, we had the NLM quantum numbers, then we learned that the speed of light is not infinite, it is constant, and we must accommodate all consequences of that, and what comes out of that is the Dirac equation, and what comes out of the Dirac equation is the electron spin, right. So, the angular momentum is then no longer just the orbital angular momentum, but L plus S, which gives the total quantum number, total angular momentum, which is J. But even that is not the ultimate angular momentum of the atomic system, because the nucleus has got a spin. Okay. The nucleus contains elementary particles, the protons, the neutrons, right, and they have their own internal spin properties. Okay. They are fermions, okay, protons and neutrons, and depending on the number of neutrons and the number of protons, the atom may have a net angular momentum which is either integral or half integral, and then you have either Bose atoms or Fermi atoms. Okay. So, when you consider the nuclear spin, then the nuclear spin I will couple to the net angular momentum J, and you will get another angular momentum which is the total angular momentum inclusive of I and J, and this is a relatively weak interaction as one would expect, because the nuclear spin will involve not the Bohr magneton, but the nuclear magneton. You will remember that the Bohr magneton had the mass in the denominator. Now you will have the mass of the nucleus in the denominator, and the mass of the nucleus is much larger than the mass of the electron. So, that makes the nuclear magneton much smaller, and as a result of that, this is a relatively weak interaction. Nevertheless, it is an important one, and this is what gives rise to the hyperfine structure coming from this interaction I dot J. So, just like you had the L dot S interaction, you now have the I dot J interaction, which gives you the hyperfine structure. Okay. And then these hyperfine structures will lead to further splitting of these Zeeman levels, and that splitting will be very small, very tiny, but that is very nice, because you can have very nice control when you look at those transitions, and some of those transitions in the hyperfine spectra of alkali atoms are very common transitions that you can control in laser cooling and other experiments in atomic physics like Bose-Einstein condensation and so on. So, that is so today's class we conclude over here.